you can probably tell from what you can see, I'm not really hiding what we're about to do. We're going to take just a little bit of time and investigate what's called the second partial derivative. So notation-wise, what you're looking at here are two examples of a formal notation for partial derivative using the partial derivative symbol in both cases. And I want to remind you all that we have certain rules of algebra that we follow, and one of those rules would be that whatever happens in the parentheses happens first. So there is another way to write this in a formal notation, but I'm going to skip right to what I would say is my preferred notation in the classroom to minimize the chance of people being confused. So what this says is you have your function f, and to take the partial derivative with respect to x. And then whatever you get from that, take the partial derivative with respect to x again. Do it one more time. So we simply just write this a second time. Now it's critical to know that this is what comes first and this is what comes second. So the one closest to the function is first, and then this one would be second. And the reason that is important is you can see this second variation of the notation. I have my function f, and I'm going to take the derivative with respect to x because this is first. Then afterwards take the derivative with respect to y. So that would be what happens second. And there are two more that are not shown on this page. You're not seeing the variation for starting with y and then doing the y derivative again, or starting with y and then doing the x derivative again. But as long as you understand that this first notation is what you do first and this is what you do second, it's not really that difficult to work from there. So we're going to try all four combinations on one problem just to get some exposure, some practice. Here we go. All right. So we're going to start with the x derivative and calculate that, and then we'll look at possibilities for what to do after that first derivative. So let's do the first derivative calculation. If x is the variable, then we have here, let's put it in the red pen, 10x. If x is the variable, derivative of x is 1, so we get minus 4y cubed. And if x is the variable, 4 times 6 is 24, x cubed y to the second. Okay. Now, if x is the given variable for this first derivative, and we want to calculate what happens if we then do the x derivative again, this would be the second partial derivative. So if x is the variable for the second one, then the derivative of 10x is 10. This has no x's in it, therefore it is constant. The derivative of a constant is 0. This does have x's in it. 3 times 24 is 72. And it would be x squared and then y squared. So this would be the second partial derivative with respect to x. Now if I started with this x derivative and then decided to take the y partial derivative afterwards, so I'm starting here and then I'm going to take the y derivative, the derivative of 10x would be 0, and this would be negative 12y squared, and x is not the variable but y is the variable, so 2 times 24 is 48 x cubed y to the first. These are not the same. I wasn't expecting them to be the same, but these would be two of the second partial derivatives. Now I'm going to keep going here a little bit further. I want to go back to the very beginning and say, well, what if we had started with the y partial derivative? What would have happened next? Well, if y was the variable, then the derivative of 5x squared would be 0 because that would be a constant. Then this would be 3 times 4 is 12 negative 12x y squared, and 2 times 6 is 12 x to the fourth y. So that would be the first derivative with respect to y, that partial with respect to y. If we begin with the y derivative, what would happen if we took the second partial with respect to y? What if we tried that again? What would that look like? We're in algebra autopilot mode now. We're just looking at a whole bunch of polynomials, not really being guided other than I'm making us do some calculations. No fantastic discoveries yet, but give me just a moment and I'll hint at some things that you should follow up with. Let's do this calculation. So start with this and then take the y derivative again. 2 times that would be negative 24x y to the first. Y is the variable here, derivative of y is 1, plus 12x to the fourth. Second partial with respect to y. Okay, now if I start with y, if I start with this, and then I do the partial with respect to x, I have to slide her up a little bit now. We're going to lose our function, sorry. If y was the variable and then x is the variable, the derivative of x is 1. This becomes negative 12y squared. And then x is the variable, so 4 times 12 is 48 x to the third times the constant y. Does that look like anything else on the page? Alright, I need some way new to shed some light on this. It turns out that these two appear to be a match. These two appear to be a match. And we won't prove it in this video segment, but it turns out to be a fact that the partial with x and then y will be equal to the partial with y and then x, given some function of x and y. We won't prove it right now, but this is sort of an important little fact. It will play a big role later in the course, but for now I'm just going to leave that as sort of a key statement. These are called the mixed partial derivatives. because we have both x and y, not one only, but both, and they're mixed in the order, doesn't matter. These mixed partial derivatives are equal. But it turns out there are some other types of properties with certain functions and their second partial derivatives. And in the textbook, there's a few references to some big differential equations that tie into engineering, fluid mechanics, electricity. I'll leave those to you guys to go explore further. We were just sort of busy in calculation mode right here. Make sure you can do the calculation, then you can go check out some more problems that follow. All right, that was fun. I wonder what we're going to get to do next.